Hello, welcome to this short video talking about meshes and how they work within Rhino and Grasshopper. If it's your first time ever working with meshes, just be aware that we're talking about this mostly because meshes are the most utilized piece of 3D data that tends to transfer between different programs. Meshes themselves are pretty simple objects. Currently I have one selected here. It's over to the left, while I just have a copy of the referenced mesh here. But if we zoom in on one of these, you'll notice that as we get closer, what looked like topography that was potentially curvy is really made out of all these kind of straight lines with all this different shading. Meshes are a collection of geometry, either in quadrilaterals or triangles, that is basically embedded as points, which are vertices, and then the connections therein, which are going to be how you get faces. There are other components to meshes. Anytime you have a face of an object, you can do a normal, which is from that center point perpendicular outwards from a plane. You can also encode colors and other data into here. We will actually use that in this video, but it's not as common within Rhino outside of some simple analysis. The reason we're using meshes as opposed to surfaces for the topography project we're working on is not because there aren't good tools for working with topographies that are surfaces. There absolutely are. Bison is a Grasshopper plugin. It does a lot of things. You can also pull a lot of data in from elk, and you can also resample meshes to become surfaces. Things that, as a NURBS modeler, Rhino tends to be better at handling, and which you have more tools to work with in Grasshopper. But oftentimes, if you're getting data from somewhere else, they're going to give you a mesh. So, for those who are curious, I have just generated this mesh off of a height field, just a black and white image that was obtained from USGS. I'm not going to cover how to do that because that's a totally different program and different way of getting data files. But I'm just going to assume you have a mesh to work with since I'm providing them for this project. In this case, we have our one mesh here. Just located in blue. And there's a lot of things you can do with meshes. First, I want to just deconstruct it to get everyone familiar with what they look like. So the common deconstruct mesh, or demesh is the other way to do this. Double clicking and say demesh. We'll bring this up as well. This is located under mesh, and it's in the analysis tool. There are several other good tools here. We will be looking at deconstruct, but face normals can sometimes be useful instead of using deconstruct mesh. Mesh edges is very useful. Sometimes face boundaries. I don't often use deconstruct face. And then there's some mesh evaluation tools. You can also create a lot of general objects in mesh form. It's less advanced than the surface components. And you can also use a handful of other analysis items such as Voronoi and Delaney meshes. Delaney meshes or Delaney, I'm not entirely sure the pronunciation, is essentially whenever you, is what Revit uses to calculate. So when you place points and it just figures out the simplest surface, you're generally setting a Delaney mesh that can make that as efficient as possible, or at least through that algorithm. There's a bunch of utilities here, such as cull faces, delete faces, unifying meshes, which has to do with mesh face, and then things like triangulate. So I'm going to pull triangulate out because it can sometimes be an important tool. We won't be using it that much this time, but I generally find triangle meshes cleaner and easier to fabricate because all triangles are planes, while quads can be non-planar. But first we're going to take our mesh, and we're going to put it in deconstruct mesh. So from here, if I hover over mesh, it will tell me there's a referenced one. It says V45461 and F45020. Those are counts of both the vertices and the faces. These will not often be the same just because you're going to need more vertices to describe how many faces you have. Some weird non-manifold geometry may have it where you have more faces than vertices. We're not going to worry about that. Those are usually very bad meshes. But generally, this will be the type of data you'll see out of a single mesh. If we deconstruct the mesh, we're going to get a handful of different things. Out of the vertices, we will get individual points. These are literally all those intersections between the lines I was showing you on the previous mesh. Mind you that these are just transformed over a little bit because I've moved it, but they're generally the same types of, and you can see that it's starting within an X direction and then it modulates. That's totally fine. It's just the way that it's organized, the data tree of vertices. It's one tree. It's just in order. You'll also get faces. Faces, in this case, will either have either a Q or a T. Q means quadrilateral, and T means it's a triangle. The quads will have 4 numbers after them. Those are indexes. So this pulls in our vertices list, that first one is number 0. That's going to pull 0, the 301st item, 302nd item, and the first item. And it's going to make quadrilateral out of those 4 points. The reason it does this is it is very efficient to store this type of data this way instead of having each of these be individual surfaces. It makes performing operations on meshes generally easier and faster. If you try to make the same surface out of control points, your surface that you have for vertices, like in the U and V directions, you are going to have many, many more pieces of information that get tied to it, and they all take longer to compute. So meshes are fast. We also have colors. I did not create this with colors. You can assign meshes things like texture maps or import them. This is off of a height field. I could bring the height field in and assign it to it. I didn't do that. I usually don't find that useful because I don't try to render in Grasshopper or Rhino, but for some it might be. And then there are normals, and these are going to be whatever shape we get, it's going to be that perpendicular line coming directly out of it. Be aware that technically there are 2 lines for that. There is a directionality to meshes. So on this mesh here, we will try to get under it. You'll notice that it looks the same top and below. You can actually, in the display properties here, come to colored back faces and then select whatever color. We are going to go with magenta because it is super easy to see. So there is a directionality. This is the functionality you find in SketchUp whenever you have like just white and then you have that like lightish blue. That is a backface type of organization, the light blue is. In this case, I've just colored it to be magenta. This is useful if you're trying to figure out if there's a problem or something in a mesh that you've made, but won't be super useful for what we're doing most of the time. So, like I said before, that there are quads here in the faces, they're Qs. We can triangulate this also. So we'll come back over here and we will go to mesh, and now we have a similar mesh, but we have many, many more faces. Should be actually double the amount as we had before. Yeah, 45,020 versus 910. So 90,010. Yeah, so it's double. If I plug this in here, we'll get a lot more. So we're seeing the points in this case. But if I go ahead and just pull out a tool to look at the mesh faces, not face normals, face boundaries, we can see that instead of being these squares, quadrangles, that we are now looking at triangles. You'll also notice as we zoom in that there is not a super large amount of reason to how these are going. There are ways to unify this. There are specific tools that actually make this very useful. Once again, it's not that important for what we're doing right now. As you get to doing simulations or other things with meshes, these may become much more important things, especially keeping them clean as you go. But for right now, just be aware that there's a difference in triangulation and quadrangles. I believe we can go back the other direction. guess is this is going to start getting kind of messy. What I should have done is taken the triangulated mesh instead of the face boundaries. My computer's probably not liking this much right now. Sure not. Excellent. So make sure then when you do this that you tend to plug in the right things. While meshes are faster generally, the amount of data and the size of the list that tend to come out of meshes mean that if you do the wrong thing, you can actually end up stalling out the program fairly easily. In this case, I may have just stalled this out completely, and I may have to start recording again soon. I do not. Excellent. It did not like it, though. Data conversion failed from curves to mesh. That makes sense. We're going to plug in this one instead. Yeah, so you'll notice that I have a different number of faces this time than I had originally. If I plug this into the face boundary, you'll notice it doesn't look so great. You'll see that there's some quads, like you can see right here and here, but it didn't pick up everything. A lot of your stuff here is going to be on ratio and angle thresholds. You will want to make sure that if you are starting from quad-related mesh and you want to keep it that way, to just try to keep it in the same range. And if you're using Triangulate, play with these or use other plugins like Pufferfish or something else that may be better at handling meshes in general. So this is all great, but why is a mesh considered useful? Oftentimes it's just because you can take those points of data a little bit more easily or more readily than if you need to create like a sampling list or you have to project points onto something. Which you often have to do with surfaces, or you have to divide them into different UV amounts. If we come down here, I have two simple scripts here. One is for testing and displaying different slopes on the faces, and the other is for showing height in basically a height map scenario, just using a custom gradient. Similarly to what we were doing before, we were using mesh and then deconstruct mesh. And this is giving us our vertices, our faces, our colors, which we don't have any, and our normals. For the heights, I'm actually just going to be using the points here. This isn't necessarily the most precise way to do this. You would likely want to take the average of 3 points for each face. I don't care about making that data structure. I think being close here is fine. And I know that everything's continuous, so it'll turn out generally well. So what I'm just taking are these vertices, which themselves are points. I'm deconstructing them, and I'm taking the z value, which is going to give me the height. You could do this also on x and y, but you'd have to have a reason why you want to go east and west or north and south. Height makes more sense. From here, we are creating some bounds, or finding the bounds of this list. So we come from this large list and use the bounds tool, and it gives us a number at the beginning and a number at the end. This becomes our domain. These are the range of numbers that we're using overall. We're going to deconstruct that so we can get a start and an end point. I have flipped over L1 and L0 here. This is just essentially reversing things for me. Instead of having red be the, on one side, it'll be on the other. It'll be higher or lower. I'm then taking the Z component here. Same thing we plugged into the bounds, same amount of data, 4,500, and then plugging it into here. And then it's going to, along this range, and with these values we just took, start sampling things. From here we're going to construct the mesh, and you'll notice that here we do get a height readout. So looking at it from the side, you get that darker blue, coming up to this yellow, going up to red. And you can even see the valleys and crags here. To me, this is a tool that I use very much in order of understanding topography, better than topo lines. You can, of course, contour this and do topo lines, but this gives you a directionality. You can also change your domain settings to skew it one way or the other, or to have it loop. There's a handful of things here, but I generally find this easier, and especially for non-architects to read height data, much better way to do this. That being said, it does look very sciencey and less architectural, so be aware that it may not read perfectly well for, a critic. But that's pretty easy. All we did, we took the mesh that we originally had, we found the heights of the points of the vertices, we grabbed a gradient here, and then we reconstructed that mesh. Notice that I'm just pulling the same V and F from the original deconstruct into the construct. We have changed nothing. We don't even have a different amount of values coming from here out of here. So this is just a very simple, take it apart, use one piece of it, put it back together. It's usually a very fast, easy way to do this. Similarly, if we look down here, we'll notice we'll have a different component that we're using, in this case, the normals. So like I said earlier, each face within here is going to have a normal based on its center that is going to go outwards, perpendicular to it, in the direction that is facing up for the face. In our case, they're all aligned upwards. We don't have any going down, so I don't have to worry about fixing any data here. But all I'm doing is I'm composing this normal, which is essentially an angle, it's a vector, with just up with the unit z. So A and B, I'm just using the angle tool to compare them. It's going to give me an angle. I put this into degrees. You honestly don't have to do this here because you're changing your bounds here anyway. But degrees just make more sense to me, so I use them. And same thing up above. We're taking the bounds, we're deconstructing them to get our start and our end point for our data, and then we are sampling them here. You can manually remap things if you want them to be between 0 and 1 if you want to. We've done this before, but you don't need to. This is just a quicker way to do it. So same gradient, same everything, and we go to construct the mesh. And now we can see that where it is flatter, here, it is generally bluish. Where it is steeper, it starts getting reddish. Now this won't tell you exactly how, say, water is going to flow on the site, but it should give you a pretty idea very quickly. There are other tools for figuring out where, how much surface area connects to water, through a lot of different methods, actually. But you should be able to tell where the main ridges are, and water is going to peak and split off of these ridges, where things are going to possibly pool up, or in this case, where they would sit, potentially, and then slide off. So using those two different components, we can kind of start breaking down and understanding the topography on a bit faster and better way than we can if we're just looking at a topography map by hand. The final thing I want to show you is this other tool, Mesh Edges here. Notice in the symbol it says 1, 2, 1, and it gives us 3 outputs. It will always give us 3 outputs regardless of the mesh you put into it. Ones, this E1, are considered boundaries. If I take this curve tool, you'll notice this is the edge. These are not connected to anything. Those are considered outside boundaries. E2 is going to be all the interior ones. It will take a little bit more to display this because it's converting them all to curves, but you can kind of see this burlappy frayed edge here. And edge 3 is for non-manifold edges, which this mesh I don't believe has any, which I consider very good. You can make a lot of problems with non-manifold geometry. So that's a basic overview of meshes, what they look like, ways you can take them apart, things you can do with them. Once again, we're doing this mostly because the data you're going to get, more than likely, from somebody else will be a mesh. You can still do more things with surfaces. There are things that are going to get very complicated and tricky whenever we start trying to take apart parts of this mesh and putting them back where they were, or just modifying them slightly and putting them back together. But as far as using the whole mesh and just doing some simple analysis, these are very quick, very easy methods of finding a value, using it as a parameter to color something, and then reconstructing the mesh. Hope that helps, and I'll see you for the next one.